that cool programmers like that write all sorts of software, including the Linux kernel. And there's a place where some function pointers are used, which are pointers to functions, I get it called, are used without, they're not checked that they're valid before they're dereferenced. And once people realized that was a problem, they scanned through the kernel code looking to see if that was ever going to be a problem. They found a couple of places where it is a problem, for example, here and here. What software does this affect? All Linux 2.4 and 2.6 versions since May 2001. So that's the whole world. Consequences. This issue is easily exploitable for local privilege escalation. Successful exploitation will lead to complete attacker control of the system. Mitigation, bloody well fix up the software. So whenever we have stuff, we always check. We don't think, I'm so clever I don't need to check now because I'm quite elite. We think, I will bloody well check every single pointer before I dereference it because I never, ever, ever want to dereference something that's invalid.
I think you guys still need to patch that on most of the machines.
Yeah, CSE is probably not patched. Yeah, and when it's patched, does that mean that we have no more security vulnerabilities? No way. In fact, a whole lot of Microsoft vulnerabilities came out on Tuesday.
They always do that.
Yeah. And if you look at some of the advisories, Microsoft's alerting, this exploit is already in heavy use. So there are things that are being actively used by bad guys. And again, they're the same sort of thing. People, stack overflowing, people not checking pointers before they dereference them. Okay, now I had some interesting things to do in the second half today. I was going to code up the bracket test, but I'm sick of coding now. I'm bored. It took us so long. It's like wading through treacle. So I'm thinking I'm just going to skip on and not do it. Is everyone happy with that? And I'm going to leave it as you as an exercise, and maybe I'll post the code. What do you think of that? So you will try and implement it. And yeah, because it'll take us an hour to write a couple of lines of code. I've either got to get faster or something. So I had some questions to show you. One was there was a question on the forum about ADTs. Let's have a look at that. Where's the main doobly? Here we go. Let's go to the forum. I'm just going to log in. And I just... It is if you know how short it is. Okay, here we are, we're logged in. Now, where was the student that asked that question? Who was it that asked? And was it Mervyn or something, a name like that? Melvin? Student asked about ADTs. Was it in teaching Q&A? Let's have a look. This was it. Mikhail. Mikhail, do you mind if I answer this in class today?
Yeah.
Where are you, Mikhail? Wait, can I answer it? Yeah. So here's the question. You're given the following header file. Blah, 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 blah. Can you change the prototype so that push and pop have a different type signature? So that they're not void. The moment the type signature, if you remember from the last lecture, we were changing the stack that was passed in. Is it possible that it returns a stack? Oh, yeah, you've written it down here, like this. So there's a couple of different levels on which we can answer this. One is, I mean, we just can't change the interface because once you've got an interface, you're stuck with it. And this is life as a computer person, that someone will give you an interface and say, write the code to the interface. And you always then think, oh, I could write it better. If I changed the interface, it would be so much better. But you just can't. It's just like given to you. You know, if I could drive on the right side of the road, it would be so much better than driving on the left side of the road. It makes so much more sense in so many ways. Damn it, I'm going to drive on the right side of the road from now on. You see, in a system where there's multiple people, once we've got an interface, we all have to comply with it, even if we think it's stupid, just because not doing it will cause all sorts of terrible things. But why don't I want to return a new stack when I pass in a stack? If it's abstract. Why don't I want to do it that way? It causes a subtle problem. Or it causes me to leak some information, or it's just something that needs to be thought about. What's the problem? Can anyone hazard a guess? Yeah.
When you do pop, when you have to like do all the memory stuff like free.
Yeah. So yeah, related to that, can I say that in different words? What happens when I pop something off the stack? I get given a pointer to the new stack, plus I passed in a stack. Does the original stack change, or does it stay the same? Because the type's abstract, we don't know. Maybe we define it so it doesn't change. But now that means whenever I change the stack, I've got to copy the whole thing across so the old one stays valid as well as the new one being created. In other words, I've got to make a new stack on every operation. Now that's dangerous and expensive because now I'm having to you make one small change to your stack, I've got to reproduce the entire stack structure. That's slow and memory inefficient. And also, the old stack now has to be disposed of as well as the new stack when we're finished. Remember, C doesn't do a house cleaning for us. So now we've got two stacks to look after. And every time I insert something, I'm creating a multiple. So every insert is essentially creating a new stack. Can everyone see that sort of dangerous? So yeah, so that's why we prefer not to do it. We could do it, but we prefer not. Does that make sense, Mikhail? Yeah, cool. With the current prototype, we'd have to run through the entire stack to get to the last item. So push and pop and top are very inefficient. Well, yes. Linked lists, if we used a linked list, store stuff at one end. And it's really easy to get to one end. And the other end is a real pain to get to. Now a stack adds stuff at one end and pulls stuff off at one end. So we have an implementation choice. Which end shall we push things on and take things off at? Shall we push them on and take them off at the easy to get to end or the hard to get to end? Easy, that's right. We could do it to the other end, but that's right, it's a serious implementation choice. With queues, it's a bit harder because you do work pushing on at one end and you do work pulling off at the other end, so you need to be able to get to both ends of a queue. So with queues we can have dilemmas, unless we implement them carefully, where it can be very expensive. Yeah. So if we were doing a concrete type, then we'd probably do that, but we're doing it abstractly, so we're doing this. Okay, does that answer that question? Yes, I think it does. Okay, good. And that was a good question, so I like the chance of being able to talk about that. Now I had a couple of things I wanted to talk about just quickly. You've got 12 coins. One of them's a counterfeit. I'm sure you'll know this problem. You don't know if the counterfeit coin weighs more or less, but you know it's not the same as the others. All the others have identical weights. You've got a set of balance scales. You're allowed to do 3 weighings. How can you do it to determine which is the counterfeit coin? You know it? You know it? You know it? I don't want you to tell me the answer, but I'm really proud that you know it, or that you've worked it out, yes. Instead, I want to do a quick sanity check. Is it possible? Let's just do an information complexity check. How much information are we getting from our 3 weighings? How many bits of information? 8 bits of information? More? 6? How many bits of information are we getting from 3 weighings? How many combinations do we get from each weighing? 3. So we do 3 weighings, we get 3 possible ways each weighing, so we get 3 times 3, 27 possible outcomes. How many bits is that? How many bits is 27 possible outcomes? What's that? Bits of information. 27. Is it 5? It's not 5. We'd need to get 32 pieces of information to have 5. Is that right? 1 bit will give us 2, 4, 8, 16. We don't quite have 32, do we? So we've got 4 bits of information. What's the question asking us? To identify 1 of 8 things. How many bits do we need? 1 of 12 things. Oh, how many bits do we need to get 1 of 12? Oh, it's close, isn't it? Well, I don't think we're going to be able to do it in bits because the rounding error is going to be more important. So, all right, let's think about it. How many different combinations do we have from the questions? 27. How many different combinations, configurations do we have to distinguish amongst? 12? Are there 12 different configurations we have to identify? It's this coin, it's this coin, it's this coin? No, there's not 12. How many are there?
We need to know whether it's heavier or
We're going to need to work out if it's heavier or lighter.
we need to know
You don't need to, but it will turn out you do need to. So yeah. So it's actually 24. You're going to have to work out whether the coin's heavier or lighter, and you're going to have to work out which coin it is. So there's 24 configurations. We've got discrimination power of 27, so it is doable. Notice, the way I gave this to my daughter, the way she tried to solve it was say, I'll weigh the first one with the first one. Now I'll weigh the first one with the second one. Now I'll weigh the first one with the third one. Now I'll weigh the first one with the fourth one. First one with the fifth one. Each weighing is giving her information about, at most, one coin, really. I mean, she's sort of getting one piece of information. She's going to have to go through all the coins. She's going to have to do 12 weighings in the worst case. But how come we can do it in 3? What's the difference in the two approaches? Divide and conquer. We are essentially, with each weighing, trying to find out multiple pieces of information about multiple coins. So we're never going to do one with one. We're going to start off with many with many. This is the heart of binary search. This is how binary search goes, remember? We try with each cut to throw away half of the possible outcomes. When you have a bug in your program, and you're trying to run your program and it's not working, I'm a great believer in the cut away the crap and see what's left approach. Comment out lines and leave the error there, and keep commenting until the error goes away. And find the smallest file you can make which has the error in it. And the smallest change you can make to make the error go away. And that zooms in really closely where I've got to be looking and focuses my attention. Do I go through the file commenting out one line, then commenting out the next line, then commenting out the next line, then commenting out the next line? No way. If I've got a 1,000-line program, it's going to take forever to find the way. So with my debugging, I always try and do divide and conquer. I try and rip out half the program and see if it works or fails, if things are looking good or bad. And that'll tell me roughly which half the problem is going to be lying in, if it's lying in just one half. And then I keep halving and halving and halving. And so rather than having to do 1,000 tests to identify the lines, I can do it in 10 tests. Does that make sense? Divide and conquer lies at the heart of all that we do in programming. Now I've got a good example about divide and conquer from a very excellent book, Programming Pearls by John Bentley. Has anyone seen or read this book? No? Oh, you should. Oh, it's an awesome book. It's a very good book. I've got a puzzle from it that I'd like us to do. He talks about lots of good things, including he talks about binary search. And he has some puzzles. Let's go through his puzzles. Puzzle A. He has 3 problems that I think that make me very happy. Problem A. Given a sequential file that contains, at most, 4 billion 32-bit integers in random order, find a 32-bit integer that isn't in the file. 32 bits is how big? Bit more than 4 billion. So you've got 4 billion numbers in the file, and you can represent slightly more than 4 billion numbers with 32 bits. So there's going to be a couple of numbers that aren't in the file. How would you solve this problem if you had ample quantities of memory? Find a number that's not in the file. That's a sort of easy warm-up. How could you find a number that's not in the file if you've got lots of memory? Are you going to search through the file for 1, then search through the file for 2, then search through the file for 3, and then search and stop when you find a number that's not there? Or when you don't find a number that's not there? You could do that. It's called brute force search, but that's a bit like my daughter with her weighing. What's a faster way of doing it? An array, we could do a time speed, there's a time-space trade-off that's often possible in computing, where you can burn up some space and save yourself some time. So yeah, we could have an array with 1 cell for every possible number. That would be an enormously big array. Maybe we could compact it and have, maybe we could, each cell in the array could be a byte, that's 8 bits. So you could store information about 8 different numbers, say, in 1 byte. But let's suppose we're doing it the lazy way, and we've got so much memory that it's ridiculous. We'd set up an array with 2 to the 32 elements in it. As we see each number and read it out of the file, we'd set that array element to true. We'd do 1 pass through the whole file, and that will have initialized to true every element in the array that is in the file. Then we do a second pass through the array and find the first uninitialized element. That's going to take us something like 2 times 2 to the 32 to work out. Okay, it's like order 2 to the 32. So that's not a bad solution. Well, suppose we didn't have a ridiculous amount of memory. In fact, suppose we've only got a really small amount of memory.
I was saying you could do something like a rating sort
byte by byte or something?
Well, you could sort them.
No.
You could sort, look, I like the idea of sorting them. Yeah. But you could sort them. And then you could move through the list and look when there's a gap. That's quite clever. But the sorting cost is n log n up front.
I was saying if you maybe just looked at the last byte of each of those integers and put them in, counted them in an array, and then looked at which one had less than 256, or whatever the value is.
Ah, yeah. I like this solution. Theo's solution is something like this, but I'm going to paraphrase it. If, and I actually didn't tell you the proper problem statement. Suppose we don't have much memory, but we can have files. We can make more files. We just don't have much RAM. Theo's solution is this. Let's create 256 files. Let's go through each number and look at the last byte of the number. And that can determine which file to put it in. And then count the number of elements in each file and find a file that's not packed out. Whichever has the smallest number, then we'll investigate that file recursively and do that over and over again, like a radix sort. And we'd have to do that 4 times.
If you just count as you're looking through the array.
Oh, you could just keep a counter for how many you've seen.
Of each of the different possible bytes.
No, you got a problem then on the second pass.
On the second pass, you would then ignore anything where the last byte isn't the one that...
Oh, okay. Oh, very clever. Okay, Theo's solution, which is actually, now I'm thinking about it, much cleverer than the solution I was going to tell you, is this. Go through the array and find the last byte that occurs least frequently. And we do that by just keeping a count for each byte. Possible byte, last byte it could be. There's only 256 counts we have to keep. Then go through the array in a second pass, filtering out all those that don't match on the last byte, because we know the last byte of the number we're looking for now. Filtering out all those that don't match on that, go through and make a count of the second last byte. We only need to keep 256 counts of the second last byte. Pick the smallest of those and repeat. It's essentially a binary search, but it's dividing by 256 every time, just like radix sort. If we wanted to make it a binary search, you see we could do that bit by bit. We could do one whole pass looking at the last bit of the number, and then look at which of those two is smaller. And if the one's ending in 0, there's less of them than the one's ending in 1, then we'll think, okay, the last bit is 0. And then we do another pass through looking at the second last bit, and then there's no. But your way's even faster. I like it.
The benefit is that a byte is easy to explain.
Yeah, byte's east and fast to get. Yeah, and you're 8 times faster as well. Yeah. So very nice. In addition to not having to do bitwise operations. So binary search or divide and conquer is a wonderful strategy to have, and we use it to solve lots of problems. Now I have a second problem from the book. This problem is this. Suppose we've got an array of n elements, and we want to rotate it. We want to take the last k off and put them over here, and we want to shuffle everyone along. How can we do that? We saw in the previous lecture that you could do that if you had a temporary space. You could actually literally copy those guys across, then copy everyone along by n into the k into the right position, then copy the temporary area out and put it back in the beginning. But that takes temporary extra memory proportional to n, potentially, proportional to k, which itself could be proportional to n, it could be as big as n. Yeah?
What if you've only got 2 different people, then can you just sort them?
If you've only got 2 different people, you could sort them. Sort them. 2 different people. You mean, not everyone's individuals, we just had 1s and 0s or something like that. Yeah. So tell me about that later on, because that sounds like an interesting algorithm. But for this problem, I want to imagine everyone's a unique individual and we can't... it's a crazy idea, zoring people. That's sort of what happens when you get married, in a way. I find that your attributes compel your partner's attributes to be the opposite in some way. It's quite crazy. So if one of you, whichever one of you is slightly more neat, is compelled to become the very neat one. And whichever one of you is slightly risk-averse, as a parent, is compelled to become the very risk-averse one. It's just you sort of have this effect on each other. It's very interesting. So I never thought of it as XORing before, but it makes so much sense now. Now I understand. I'm going to write a self-help book. So there are several different ways of doing it. My challenge to you is, without looking up Bentley's wonderful book, can you come up with a linear time algorithm which shuffles everyone along, which is as close to in place as you can possibly be. So it only needs a constant additional amount of memory. Make it as beautiful and simple as you can. I predict there's two different sorts of solutions we're going to be seeing. So when you come up with your solution, if you're not looking at it and it's really beautiful, look again for another solution. Though, pat yourself on the back. Another puzzle I wanted to give you was this. I remembered this a few weeks ago because we were talking about the paper folding problem. Do you remember that? We're talking about how exponential growth and how if you folded a piece of paper n times, the thickness was 2 to the n. So very, very quickly, no matter how thin the paper was when you started, you'd end up with an implausibly thick thing that couldn't be folded. And you were telling me about this excellent thing on Mythbusters. And that reminded me as I was going home about a wonderful puzzle. So the puzzle goes like this. And the story behind this puzzle was one day I was waiting at Town Hall Station to meet a friend. This was in the old days when mobile phones didn't exist. So all you could do is stand there just waiting for them to turn up. And so I was waiting at this rendezvous point and I was thinking, I'm bored, I have nothing to do, I don't know how long I'm going to have to wait here, and I didn't bring anything interesting to do, and I can't go away or the friend will turn up and I'll get in trouble for not, you know, will there be some dispute about who was here first or something. So I'm stuck on this spot, but I'm bored. And then some religious nutter gave me a little pamphlet that was this long, thin piece of paper. And it was just like, wow, thank you. So I had a piece of paper and I thought, what's an interesting thing I can do with a long, thin piece of paper? And I folded it up and then I unfolded it. It was enormously fun. I was practicing binary search because, of course, this whole idea of dividing the problem in half each time, it's very compelling. It's remarkable how quickly that zooms it down to a very small problem. But as I unfolded it, I noticed that the fold patterns were ups and downs. And that was very interesting. And I thought, gee, what's the relationship between the ups and downs of the fold patterns when you unfolded and whether I folded it up or down when I was folding the paper up? And then I thought, wow, that's an interesting problem. And then I tried to generalize it to 2 dimensions, which is if I have a piece of paper and I do a series of folds, horizontally or vertically, on that axis or that axis, in or out each time, and I somehow define it so I know what the paper looks like after a fold, which bit remains unchanged and which bit moves, can I come up with some sort of function that predicts what the network, the lattice of up and down folds will produce when you unfold the thing? So my challenge to you is, can you write a program that, given a sequence of fold moves, draws a picture of what the thing looks like when it's unfolded? Does that make sense? It's a very interesting problem. And I vaguely remember in my younger and brighter days, I realised that folding the long, thin piece of paper gave me a solution to the Tower of Hanoi problem. Does everyone remember the Tower of Hanoi problem? You got some discs and you've got to move them from here to here. And the rule is the discs are all different size. You can never put a smaller disc on a bigger, you can never put a bigger disc on a smaller disc. And you can only move one disc at a time. And we looked before, this has 2 to the n moves to move n discs across. But it turns out if you fold a piece of paper, and the recursive solution to Tower of Hanoi is move n minus 1 things across, then move the bottom, then move n minus 1 things across the remaining thing. So you've sort of got to move this way, and then you move one thing across, then you repeat that original move. And if you look at what happens when you fold a piece of paper, any subsequent folds that happen here, when unfolded, will also be happening here, but in reverse order. I mean in reverse up and downness. And also in reverse order stackwise, first and last. And if you think about it, that's exactly what you have to do to move things. Essentially, it's giving you all these moves on the top, and then this fold corresponds to moving the bottom guy across, and then all these reverse moves on the bottom too. I worked that out when I was young. I was really impressed. I can't remember the details, so if you could work it out for me again exactly how it works, I'd be your friend for life. So that's my second puzzle to think about. Now, the last thing I want to do now is resolve a puzzle that I gave you guys back in week 1 or 2. Week 2, I think. Remember when we were looking at insertion sort? And I said, insertion sort of has 2 aspects. One is finding the insertion point, and the other one is then doing the inserting. And if we're doing it on an array, the annoying thing about doing the inserting is that everyone has to shuffle along one, and that's very expensive. And if we're going along one element at a time trying to find the insertion point, that's very annoying too. That's going to be, on average, we're going to have to move halfway along. So we're going to, on average, have to move halfway along with comparisons to find the insertion point, phase 1. And then on average, we're going to have to move everyone along, or half of the guys along by 1 in phase 2. So that's, but they're both order n. And that's very annoying. And we looked at ways of speeding it up, and we saw 2 different ways. One was we could implement it as a list. If we implemented it as a list, what did that speed up for us? Phase 1 or phase 2? Speeds up phase 2, because now we don't have to shuffle everyone along. We just break one chain on the link, insert the new guy and re-glue some pointers, and everyone has moved along. So phase 2 is super fast, but phase 1 still involves toddling along the list one at a time, trying to find the insertion point. It's very slow. Then we thought of another way of speeding it up. And what was that? Do you remember? Binary search. If it was on an array, lightning fast. We can binary search and find the insertion point, not in linear time, but in logarithmic time. But damn it, that only works on an array. And now we've got to move everyone along. So we had these 2 ideas for speed ups, but each of them still left us with the other phase being linear. And the challenge question I asked you is, can you think of a way, some sort of data structure that's not a list, there's not an array, that lets us do both these things? Find the insertion point in logarithmic time, or super fast, but do the insertion super fast. And I left that as a challenge to you, and I don't know if anyone's worked it out. Put up your hand if you have. Well done. Anyone? Is your hand up? Is that you? You worked it out? No, no. Your hand's up? You got it? Who else? You again. You got it. Okay. Well done, guys. Excellent. Okay. Do you want to tell me? Call it out at the same time.
Binary search tree.
A binary search tree. You said it after him. You're very clever. This is what I do with my wife. We say, who's going to have to do the dishes tonight? And we're on the phone. And I say, I'll toss you for it. And she says, I can't trust you to toss a coin over the phone. And I say, well, tell you what about we both toss coins at our end, and then if they're both heads or both tails, I'll do it. And if they're mixed, then you do it. And that way, neither of us has full control over what happens. No matter what one of us throws, the other one can make it go the other way. And she said, that seems fair enough. And then we toss it, and I said, I got heads. And then she said, oh, I got heads too. And I thought, damn it, I didn't think of that protocol very well. So yes, the answer is binary search tree. So let's just have a quick look at a tree. A tree has both of these delightful properties. The rule with a tree is you insert a number into the tree, you compare it with the value in the node. Trees are recursively defined as either being empty, a tree is either empty, or it's a node with 2 subtrees. That's a recursive definition. It's either empty or it's something that involves 2 other trees. Something that's a tree involves 2 trees. Okay. We want to insert something. Suppose I want to insert 6 and the item in the node here is 42. The rule that we follow with the search tree is if it's the value at the node I'm looking for, I'm done, I finish. If it's not, this one comparison tells me which half it will be in. So it's smaller than 42, so I know the 6 has to go into this tree. So I just recursively repeat that operation. So to insert 6 into a tree, I compare it with the top node. If it's less than the node, I insert it in the tree on the left. If it's greater, I insert it into the tree on the right. Notice this is going to give us the logarithmic nature. Every time we're going to throw away half the options of where it can be. So if my tree's got, if this is equal size to that, then I'm throwing away half each time. It looks like binary search. It's going to take the depth of the tree is going to be log n. It's going to be log n. I better write my little caveat. It's going to be log n if what? I said it before, but I said it in small print. And no one looked sufficiently horrified. I think I got away with it saying it. But to be honest, I should probably say it in slightly bigger print. This will give us logarithmic time if, yes, if both subtrees are about the same size. Okay, now there's a bit of wiggle room with about, and anyone doing discrete maths will hopefully learn enough maths in that course. Am I right in thinking that? Who's doing discrete math? Right now? Is anyone doing it? Did anyone do it last semester? Yes. Do you learn enough? Do you learn the master theorem, or do you learn enough to solve recurrences to let you work out This? No. Oh. Well, is there anyone, Rupert, what course teaches you that? What's that? Well, don't you see that in discrete? What about the proof of the master theorem? Well, the general result that the master theorem summarises. Oh, man. Okay, sorry guys, you're going to have to wait 3 years. But then at the end, the reward is you get to do a course with Alex, who's this crazy, hysterically brilliant and grumpy Russian guy. He's the funniest person and the cleverest person in the whole world. And have I told you the story about him in the toilet? Did I already tell you that? Okay. I've got to tell it in such a way it doesn't tie back to him. So there's a lecturer in the school that one day came up to me really earnestly and said, "Oh man, I've just got to warn you about radio mics." And I said, "What do you mean?" He said, "They're wonderful, but I had a 2-hour lecture and during the break, I went to the toilet and it was really hard and I was straining and moaning and trying really hard and when I came back in, the class was ashen-faced and silent." So that was very funny. You guys aren't laughing, but it had me on the floor giggling in hysterics. So yes, so certainly if you ever have him, ask him about that, but don't say it came from me. So if they're about the same size, then this will work. That's the small print. Shh, 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 shh. I'm going to hide that small print for now, but you can't forget that. So if they're about the same size, we can find the insertion point in logarithmic time. And for a tree, because it's a dynamic data structure, it's not like an array, we don't insert by shuffling everyone along. We just insert by mallocing a new element and joining it in. So insertion happens in constant time. So we're getting a logarithmic lookup and a constant time insert. So that is a beautiful structure. So tomorrow, and it's based on a binary search. So tomorrow's lecture, we're looking at trees. I'll see you then.